Today's topic is Bohr's model of the atom. And if you're one of my students, I recommend you print out the note sheet that goes along with this lesson before you continue. So previously, we learned that Rutherford came up with a nuclear model where he used his gold foil experiment to determine that there was a very small positively charged nucleus in the center of the atom, but most of the atom was empty space. Unfortunately, Rutherford's model could not explain how the electrons don't get pulled into the nucleus, because if electrons are negative and the nucleus is positive, there should be a very strong electrostatic attraction between those particles. And classical physics tells us that they should be drawn and attracted to each other in less than a fraction of a second, but that doesn't happen. And it's going to fall on one of Rutherford's students to come up with a model that can explain how these electrons stay out in the empty space and don't get pulled into the nucleus. And that student's name is Niels Bohr. And in 1913, just a few years after the gold foil experiment, he presented the model that he called the planetary model, where the electrons are going to be in fixed paths or orbits, and if they orbit around the nucleus, then they're not going to collapse into the nucleus. In a similar way to the fact that the sun has a very strong gravitational pull on the Earth, but we're not catapulting into the sun right now because since the Earth is revolving around the sun, we kind of fall around it all the time. We're not going to crash into it, and we're able to stay in a fixed path that we follow around the sun on a yearly basis. So his discovery, we're going to write down, is that the electrons orbit the nucleus in fixed paths or orbits. We can also call those principal energy levels, which we can abbreviate as PEL. We can also call them shells. So in Bohr's model, he pictured electrons in these orbits, and the orbits or the energy levels that are closest to the nucleus would be the lowest energy levels. And then radiating out from the center, you would have larger and larger energy levels as the circle got bigger, and the farther out you move from the nucleus, the higher energy those energy levels would have. And Bohr theorized that electrons have to fill the lowest energy levels first. The ones with the least energy have to get filled before you can fill higher energy levels. And when all the electrons are in the lowest possible energy level, he considered that the ground state. Kind of like if you're thinking of standing on the ground, that's like as low as you can go. You're at ground level. That these electrons could absorb energy. If they got zapped with high energy electricity or a high energy flame, they could absorb energy and they could jump up to a higher energy level, jump out of their original energy level and jump farther from the nucleus into a higher energy level. And he called that the excited state, when an electron absorbs energy and jumps up to those higher energy levels. Now there are some rules to this. The first one is that the electron has to come back down to the ground state. It's kind of like if you were to jump up into the air, you can't stay levitating in midair. Gravity is going to pull you back down and you're going to return to the ground. And he pictured the electrons doing the same thing. They could jump to these higher levels if they absorbed energy, but it was a temporary move and they were going to have to fall back down to their original place at the ground state. And when these electrons fall back down to lower energy levels, they're going to release energy. And if that electron happens to land on the second energy level, principal energy level number 2, the energy that it releases is going to be in a wavelength that our eyes are going to be able to see without any extra equipment, and it's going to be visible light to us as it returns back down to the ground state. So before we start looking at some of the evidence for Bohr's model and for the ground state and excited state, we need to talk about a couple of vocabulary words. And one of them is the spectrum. And spectrum is a pattern of light that is created as the wavelengths of light or the colors of the light are separated as the light gets bent. So we get a pattern of colored lights as the wave is bent. And a good example of that is the rainbow. It's the same thing as when sunlight hits a crystal. So white sunlight goes into a crystal, and again, it's changing the medium that it's flowing through. The light is going to get bent, and the different wavelengths or colors of the light are going to separate out, as you can see on the picture on the right, and we get the red, orange, yellow, green, blue, violet, or that Roy G. Biv pattern. And it says here that white light is polychromatic. The prefix poly means many, and chroma means colors. And that tells us that white light actually contains many colors. So if we looked at white light through a spectroscope, which is an instrument that has a thin film diffraction grating in it that has little slits. So as the light goes through, it bends around the corners and it's going to separate all the colors. We would see something very similar to the rainbow that we saw coming out of the crystal just a moment ago. And we call that a continuous spectrum because it contains all the colors of the rainbow. There are no colors missing. Each of the colors blends right into the next color seamlessly. There are no dark spaces between colors and there are no missing colors. And so that would look like what I'm drawing here right now. All the colors of the rainbow, Roy G. Biv, right up next to each other, and every color is present. Not every source of light is going to be a continuous spectrum. We have things called gas discharge tubes, which are a different type of light bulb, which actually is just filled with an element off the periodic table as a gas. And when electricity hits it, the electrons in those atoms are going to get excited, jump to higher levels, and when they return back to the ground state, they're going to give off colors. And when that happens, we don't have a continuous spectrum. We might have something that looks like this spectrum. This is the spectrum of mercury. So when the mercury electrons get excited and they come back down, we see a very distinct bright green line, and we see a very distinct blue line. And there's no colors in between. There's a big gap, and there's black on both sides where there's colors missing. We're not seeing every color of the rainbow, we're seeing specific colors. So I'm going to draw that in my little box here under bright line spectrum so I remember what it looked like. And a bright line spectrum, we get distinct bright lines of color. Not all the colors in the rainbow. The colors aren't touching each other. We have very distinct bright lines. And these lines are caused as the electrons return back down to the ground state. Remember, as they return to the ground state, they release energy. And if it lands on energy level number 2, we're going to be able to see it with our eyes. So we call this a bright line spectrum, obviously, because we see bright lines of color. It can also be called an emission spectrum because these lines of color are created as the electrons emit or give off energy as they're falling back down to the ground state. And an important thing about the bright line spectra of the elements is that they're like a fingerprint. They are very unique to that element. It's like their signature. Each element has their own unique spectrum. No two element spectrum will be the same way that for people, no two people have the same fingerprints. So we can identify people by their fingerprints, and we can identify elements by their emission spectrum. So Bohr's going to use this information in his experiment where he is analyzing the spectrum of hydrogen. And when he does that, he noticed that there is a bright line spectrum. I'm going to put a hydrogen spectrum up here. You can see that there's a violet line. There's like a bluish green color. That particular color is called cyan. And there is a red color. And it's a bright line spectrum because we don't see all the colors of the rainbow. We have gaps between the colors, and we have very distinct bright lines of color. And I'm going to draw that again on my notes so that I can remember that the spectrum had a violet line, a cyan line, and a red line. So here we have an atom of hydrogen, and we can see that there's only one electron because hydrogen's atomic number is 1. So if it only has one proton, it's going to have one electron. In the ground state, that electron has to go into the lowest energy level that can hold it, which would be energy level number 1. But if we were to zap this atom with electricities, that electron can absorb energy and it can jump to higher levels. And when it jumps to these higher levels, now it's going to be in the excited state. And we've already talked about the fact that the electron cannot stay in the excited state. It's going to have to come back down to the ground state. And the electron can come back down in many different ways. It could come down one level at a time, like little baby steps, take each step, go from 5 to 4 to 3 to 2 to 1. Or maybe it goes from level 5 right down to level 1 without stopping anywhere along the way. Now, Now it's back at the ground state, and I made that line dotted to show the path the electron took coming back down to the ground state. And the dotted line represents that that would be an invisible release of energy because it never stopped at energy level 2. Remember, in order for us to see it, it has to land on energy level 2. So this drop is not going to create a visible line for us in the bright line spectrum. Now, hydrogen itself only has one electron, but inside a gas discharge tube of hydrogen, there would be billions and billions of atoms. So there's going to be billions of electrons getting excited and coming back to the ground state in each of these different atoms all at the same time. So I'm going to put that electron back up in the excited state and show that there's other ways that electron can fall back down. Maybe the electron goes from energy level 5 straight down to energy level 2, and then it pauses there. That drop of energy is a fairly big drop. It's dropping over 3 levels, and that's going to create a violet color, which is a rather high energy color within the visible spectrum. So Bohr theorized that a drop from 5 to 2 would create a violet line. And then, of course, that electron can't stay on energy level 2. It has to continue all the way down to the ground state. But that's going to be invisible to our eyes because we only see it when it lands on energy level number 2. Now, there might be other electrons that go from energy level 5 to energy level 4, which would be an invisible to our eyes transition. But then if it went from energy level 4 straight to energy level number 2, that's going to create that cyan color. It's a medium jump. It's jumping over 2 energy levels. So it's going to release a medium amount of energy, which would correspond to that blue-green cyan line in the visible spectrum. And of course, it can't stay in energy level 2. It's going to have to go down all the way to energy level 1. And of course, that transition we're not going to see because we can only see it with our eyes when it lands on energy level number 2. Now, there'll be other electrons in that tube that they're going to drop maybe from energy level 5 to 3. Which would be invisible. We don't see it unless it lands on energy level number 2. And then it could go from 3 to 2, which is going to be a very small drop in energy. It's going to release a small amount of energy, which would correspond to the red line in the visible spectrum, because red is a low energy color within that visible range. And of course, the electron still has to make its way all the way back down to energy level 1 to return to the ground state. So we can see here that with Bohr's model, all of the colors that are in hydrogen spectrum can be explained. A big drop in energy creates a violet line, medium drop creates cyan, and a small drop creates the red line. So let's add in our notes. Under discovery and evidence, we're going to fill in the evidence that Bohr had for his planetary model. And the evidence would be that each colored line in hydrogen spectrum represents a specific drop between energy levels. The purple was from 5 to 2, the cyan is 4 to 2, and the red would be from level 3 to level 2. And Bohr also thought of these electrons as making quantum jumps to get from one energy level to the other, because the electrons are going to absorb energy and release energy in discrete bundles or packets that he called quanta. And for the electron to be able to make this quantum jump, it has to have the exact amount of energy. It can't jump to the next level if there's not enough energy in that quantum to get it all the way to that level. And if there's too much energy, they can't overshoot the level. It's kind of like when you were playing a game maybe of Sorry as a child, where once you're trying to get your game piece from the safety zone into your home spot so you can win, you have to pull a card that has the exact right amount. For example, in this picture, that game piece needs to get a 5 in order to get home. And if they pull out a 6 or a 7 or an 8, that's too much and they don't get to move. They have to wait for their next turn. Same kind of idea with the electrons. They have to have just the right amount of energy bundled in that quantum in order to be able to get to the next level. Thank you so much for joining me today. I hope to see you on our next lesson, where we talk about the limitations of Bohr's model and how it evolved into the quantum atomic model.